Okay, so semiconductors refers to a class of material that is somewhat conducting. That's what it was, semi. And you can actually use electrical means to turn that into a conducting state, or you can use the same means to turn this into a non-conducting state. And that is similar to flipping a switch in, let's say, a household light switch. You can turn it on, turn it off. And the switch is basically the heart of all the computation that's happening in computers, in your cell phones, in all kinds of things, or even you want to roll up the windows of a car, you turn on a switch, and not a physical switch, but an electrical switch. So that's basically what semiconductors are about. It's sort of like shorthand for electronic devices that are really tiny and that could be served as a switch. And that could also become turned into devices that can store information, store ones and zeros, that's memory devices. They can also be used for many other things, and I'll go on to talk about that. So as far as where semiconductors are used, basically anything that requires electricity, either things that you plug into the wall with a plug in a wall, a socket in the wall, or something that you use a battery to power it up. Batteries for cell phones, batteries for cars, right? And cars run on batteries these days. So anything that uses electricity probably has a chip in there. So that means that, well, we use electricity everywhere, from things that like refrigerators, or things that move like cars, or things you put in a pocket. So basically everything that we use. So semiconductors are basically everywhere. And to take it into the semiconductor products, you can roughly divide them into several types. One is what we call logic devices, namely things that you do to compute. And the other one is memory devices, things that you use to store information. And there are actually two classes. One that stores information somewhat temporarily, and the other one that stores information for a longer time. And you can think of it as long-term memory or short-term memory, right? And the third kind is a little bit diverse, and it covers a wide range of things, from devices that can handle very high power or high voltages, those that you use in, for example, in power systems that transmit and store power, energy, and or the sensors and actuators, sensors that senses either light or temperature or your motion. Those are sensors, and also actuators that actuate things, that turn things like motors and things like that. And of course, image sensor is one prime example of sensors. We're doing this video conference in here that uses an image sensor, which basically is a semiconductor chip. And we called, from an industry point of view, we kind of lump all these eclectic chips together into what we call specialty technologies, specialty semiconductors. So basically three kinds: logic that do computation, and memory that stores information because you need information to compute, and the specialty, which is an eclectic collection of everything else, basically.
Right.
It's like foundries. Foundries are basically companies that produce these semiconductor chips, actually manufacture those semiconductor chips. That TSMC in Taiwan is the market leader right now, with a very large market share. And the other leading companies are Intel and Samsung. Intel is based in the US, Samsung is based out in Korea. In terms of memory chips, there's a variety of companies, Korean companies like SK Hynix and Samsung have a lot of market shares, and as well as Micron Technologies in the US. And also in Japan, there's Kyosha, which formerly was from Toshiba, and Kyosha collaborates jointly with Western Digital in the US. So those are the kind of major companies that are in memory and logic space. In terms of specialty, because it's a really eclectic collection of companies, there's just a variety of companies everywhere. For example, for analog kind of devices, and there is analog devices in Massachusetts. There is Texas Instruments in Texas, and of course TSMC produce a lot of these specialty technologies as well. And of course, I forgot about in the logic space. Of course, Global Foundries in the US also is a player. And Global Foundries also play a lot into these specialty technologies as well. So it's kind of like roughly the landscape. If I miss any particular companies, my apologies ahead of time. I'm really glad you pointed this out because this is one of the major sources of confusion in the media and also in public discussions. When I read a news article or listen to a news forum, they often say chip companies, and they'll say, okay, chip companies XYZ to produce these chips, but well, oftentimes they didn't make a clear distinction about the design of the chip versus the manufacturing of the chip. Now, oftentimes in the media, people will say, "Oh, chip companies such as NVIDIA and Qualcomm and AMD and so on make these chips." Now, I would actually argue with them; they did not make the chips. They designed chips. So oftentimes you read, chip makers like NVIDIA and Qualcomm. Those are a great source of confusion because they are not chip makers; they're chip designers. They don't make the chips. It is Intel, Global Foundries, Samsung Foundry, TSMC. Those make the chips. So we have to make that distinction very clear because that creates an impression that American companies such as NVIDIA, AMD, and Qualcomm, and so on, are leaders in chip making, which is a little bit of confusion, and that is not appropriate. So to answer your question, the chip designers, there are actually two kinds of chip designers. One is the chip designing companies that make market-facing, customer-facing products. And you can include in them Apple, for example. They design chips that go into cell phones, their computers, and so on. And as a consumer, you could buy them and so on. And same thing with NVIDIA. They make graphics chips. You can plug them into your computer and play games with it, and fancy video games. And those are products that you can buy directly from them. And there are fabless chip makers, well, not chip makers, chip designers that design chips, but then they go into someone else's system. Right? For example, Qualcomm, they design chips that goes into the cell phone. Qualcomm does not make a cell phone themselves. They provide chips for cell phone manufacturers to use the chip, and then they go into the cell phone that people buy. So there's this, little bit of distinction between two kinds of chip designers also. And the companies are very like Apple and even Tesla. They are making cars, and Tesla design their own chips. And so those are companies who design their own chips for their own system. This we call, industry, they call them system companies. They build the systems. And then there are the other chip fabless chip designing companies that design chips that go into systems. Companies such as Qualcomm, Broadcom, many of those companies that are designing these chips for people. Everybody is doing everything in the same place, including at the earlier times, before my time, companies like IBM would make their own semiconductor manufacturing machines. And then they will make the machines will make the chips will go into the computers, the big iron computers that they said that the System 360 in the 60s and 70s. And so the companies would do everything from top to bottom. As time go on, companies realize that they're not very good at doing everything. They probably are very good at doing something, but not everything. So then the industry started to differentiate. There will be companies who are very good at making equipment for making chips. There are companies who are good at making chips itself. There are companies who design the chips, and there are companies who actually put the chips into our systems. And the various companies would pick various combinations that they are good at and to do that. And so for companies that they would design and make the chips themselves, they would call them, sometimes you see something called integrated device manufacturer, the IDMs. And those classes of companies are like Intel, and previously IBM does that, and Texas Instruments for them, for example, for their analog products, they do that themselves, and analog devices do it the same way. So those are the IDMs, integrated device manufacturers. And then somewhere in the 80s, people realized that it would be more, from running the business point of view, more efficient to separate the design and the manufacturing of the chip, and there rise what they call the foundry model. Namely, your companies will be specializing on the design. There's somebody who specializes on the manufacturing, and therefore deriving larger efficiency in running the companies and running the business. So that's the foundry fabless split that occurred around the early to mid 80s, and a prime example of that is the founding of the TSMC in Taiwan by Morris Chang, who used to work at Texas Instruments, which is a integrated device manufacturer. Good, and let me explain the difference between leading edge chip and legacy chip first, and then I will lead to. For the legacy chip, there are two branches that I need to explain because it often get conflated, and therefore the discussion about legacy chip get mixed up, and that's not good. The difference is for leading edge chip, that means that you are at the leading edge of the technology development and research. So this is the newest products, the fastest, the most energy efficient computing chips that you can find. For example, you buy a phone, and this year you have a phone, and next year you have a newer model of the phone that has longer battery life, can do more things because they have the newest generation of chips. So those system products will often drive the development of these leading edge products, and those are the most advanced, most expensive products, semiconductor chip products that you can find. And so that's the leading edge chip. And then you oftentimes hear kind of names such as 5 nanometer chips, 3 nanometer chips, and so on and so forth. And those are just labels for these technology products, such as you got a car of Model 5, Model 3, Model 2, and so on and so forth. So you can think of these names as kind of models, right? And generally speaking, the smaller the number, the better, right? And there's a long history about that, and we'll go into that sometime later when people are interested. But to understand that, they are identified by numbers of nanometers, and then the smaller is generally the better. Okay, so that's the leading edge chip. So the legacy chip means that, okay, so now you have a semiconductor foundry or some integrated device manufacturer that produce a generation of products. And of course, then time moves on. A few years later, that particular product that you develop is getting old because there are other newer generations that performs better and higher energy efficiency and so on. But The flip side is these older quote unquote older products are cheaper to manufacture. Now, because we already know how to do this, all the equipment that you use to fabricate the chip or manufacture the chip are all depreciated. So you don't have to pay for depreciation. You're just printing money right now. So those are what we call the legacy chip, the older generations of technology, the mature, what sometimes you can see mature node. Node is a name, a technical name, or for these technology generations. So you can see a mature node or legacy chips. Now, among those legacy chips, there are actually two very important distinctions. One is simply older generations of logic chips or memory chips that is just past their prime, but still useful. They're still useful, and you use it because you don't need the performance, don't need the energy efficiency, and you just want lower cost, and that's one of the main reasons why they're used. Second would be that oftentimes manufacturers would say, okay, now I know how to make these chips. I can use a similar technology as a base and develop other functionality that add on to the original purpose, which is computing. And we have many examples of that, and that gives them special capability, such as the image sensor that we have. We're recording our video on the image sensor. They are done on these mature, what they call mature nodes, but they are not just simple, no change the technology. One actually spend a lot of time developing adding on new things to it to make it to be able to capture image much better than before, or handle higher voltages, or make a response to high frequency signals for RF or communications and so on. So people spend a lot of time and resources and energy and spend a lot of research dollars to make that do these other things, but they are based on a previous generation of technology. Why are they based on a previous generation of technology? Because then you're starting from a cheaper base. You don't start with really a fancy, costly platform. You start from a lower cost platform. And so that's kind of two different, when people refer to mature node or legacy nodes, oftentimes they don't make a distinction like that. But this distinction is really important because you do spend a lot of time and energy to develop these other special capabilities.
Right.
Question. I don't have a lot of insight into how companies actually do their work and so on. But what I could say is that which is the kind of technology leader or market leader at any one point is a very temporary situation. It is basically the leadership is fleeting, basically. We have right now in the logic space, three major companies competing for the technology leadership in the logic, advanced logic, namely Intel, Samsung, and TSMC. And I would characterize it as running neck to neck. And one of them is slightly ahead of the other ones. And I would say at any one point in time, if any company do something really fantastic, they could move forward and become the leader. Or flip side, if somebody who make some mistakes or make some wrong calculations, they could fall behind. So this is not, I would say it's not a permanent situation. It is a temporary situation. And just like in a horse race, you can be ahead, you could be slower at any point in time. You know, there's no end point in this race either. I should say that. Well, China has already joined the race many years ago, right? They started their own logic foundry, specifically SMIC and several other smaller foundries as well. They also started some memory companies like CXMT for DRAM. for making memory devices, and also YMTC to make NAND flash, the long-term data storage devices. They're already in the race, right? And they started a little bit later than the rest of the world. And so as kind of staying on the analogy of a race, you have a marathon and somebody started first and somebody started later. So I would imagine it would take a little bit of time for somebody to that started later to catch up to the rest of the world. And how much, as far as how much time it would take, it's really a strong function of a number of a variety of function kind of parameters, availability of talent, availability of capital, management systems, and so on. It's really hard to say. And in this race, they are clearly behind the rest of the world right now as far as what kind of things they could do to accelerate their progress is really a variety of things. Putting in capital or investment is one thing, but it's not the only thing. Very well possible, and this scenario is basically a business decision. It's not so much a technology, not gated by technology, because those older technologies, the ways to manufacture them and the way to design and manufacture are pretty well known. And so there's not really anything that prevents any particular country or regions, in fact, is not limited to China. It could be in one day, maybe Vietnam or whatever, or Brazil could one day do this and as well. So it is not a matter of technology capability, it's a matter of business situation. So if one country or one region could create a business environment that allow them to dominate the market, I can totally see that happening. But I agree with that notion that it is as important as oil, in the sense of oil is a source of energy that the entire world depends on, and chips runs basically the entire world from your rolling up your windows in the car to doing the most advanced computation for AI and for chips for 5Gs and those. In that sense, yes. At the same time, chips are very different from oil, and you can maybe I talk about in some of my advocacy for chips also, which is chips needs to continually advance in order to show its value, in order to provide its value to society. And oil, they have been in the ground for millions of years and they never changed, although one could argue that the technology to explore the oil do change, but the oil itself does not change. And so the chips, for example, you can stockpile a lot of oil. Put a stockpile in there, and if you need, in case of emergency, you can just draw upon the stockpile, which the US does also, and many countries do. But to stockpile chips is only effective to a certain extent because technology will get old. Would you like to stockpile your cell phone so that you don't have to buy a cell phone for another 10 years? You would not, because the technology advances, these chips can do more things into the future. So you cannot stockpile chips to a certain extent. You can stockpile for a little while, that works, but which is what China is doing right now. They're stockpiling a lot of chips in anticipation of more restrictions and export control and so on. But it can only work for us to a certain extent. So that's the real difference, clear difference between like oil and chips. You need to constantly renew it, and therefore the research and development of chips is just as important as the manufacturing of the chip because of this particular attribute. Because if you move a fabrication facility in let's say in the US, you only have the capability to fabricate this particular kinds of chip, and you have no way to provide a future chips. About supply chain itself first, right? The chain consists of a long, really long chain, starting from the basic material. You need to mine the material, you need to purify it, and the materials itself, and also the materials that you use to fabricate the chips, chemicals and gases and so on. So starting from that, you've got materials, and then you have manufacturing equipment that they use to produce the chip. Take an analogy of a kitchen. You need to go to the market to buy the material. You need to have a kitchen that have a stove, that has an oven, and pots and pans. Those are the equipment. And then you need to have companies that develop the technology. They need a chef that could come up with a recipe, right? And then you will have you need to manufacture those chips, and that's the manufacturing aspects of it. And keeping on the analogy of a restaurant or a kitchen, you have a chef who come up with a recipe and nice dishes. But then you have a franchise restaurant, right? Then you need to have the manufacturer of those food, a new burger or whatever, right? And then after the chips, and then you have the designing of the chip. How do you configure the chip? You want to have a burger that has a tomato on the top or tomato on the bottom. That's different, right? So the design of the chip, and then you have the system companies who use the chips to do something useful, right? So this is an entire chain, and along the chain there are many companies that provide the tools to do things, tools to manufacture chips, tools to design the chips, and those are all part of the chain. So now when we talk about a supply chain, that means that if one link of the chain is broken, you already have a broken supply chain. Doesn't matter if the rest of the chain is intact or continuous, you just need one point, it's broken, then you cannot make anything. So in other words, any particular part of the supply chain is broken, you don't have a complete supply chain, and you have a big problem, okay? So that's part. As far as the various pieces of the supply chain, and you probably see in many discussions in the public media that some countries or regions are really good at doing certain things. For example, in Japan, they're very good at materials and also semiconductor equipment. In the US, there are many major semiconductor manufacturing equipment companies. Also, electronic design automation tools to help design chips in a very efficient way. They're all kind of headquarters and based in the US. And also many of the system companies who put together chips and design chips and also put together systems are based in the US. Many of them are in the Bay Area here, right near Stanford. So those are the kind of strengths that that various regions would have. For example, in the Netherlands, they have a very dominant company that makes what they call the lithography machine, who is part of the manufacturing process of the chips. And in Korea and in Taiwan, they are very strong in manufacturing those chips. In Korea, they manufacture the memory chips. In Taiwan, they manufacture the logic chips. And so there's this supply chain, and globally there are regions that are good at it. But it doesn't mean that once you deleted that region out of the picture, then you're quickly in trouble. You could be in trouble temporarily on a short-term basis. But I think if any supply chain is disrupted, then in most cases the rest of the business community will come together and fill in those spaces, because then if somebody is deleted out of it, you created a vacuum, and so over time Now, the question is over what time, right? So some will take longer, some will take shorter, and over time, that space will be filled in. The supply chain is so diverse and so complicated that no one country or region is big enough and robust enough to be completely self-contained. That's a scenario that you describe, which probably is described by many in the discussion, is entirely impossible. Because for several reasons. One is for the reason that you just described. The supply chain is so complex that any particular company would rely on the rest of the supply chain to be completely operational. And so if the rest of the supply chain is absent or not cooperating with that particular company or that region, that is not gonna the company is not going to be able to operate. That's the first question. That's the first kind of degree. Now, a further consideration, which most discussions like that did not go into, is the level of trust that is required in this business. For example, in a foundry, you would have many thousands of customers, and many of the customers are competing against each other. And the way a foundry work is that they need to work with all the customers. Many of them compete with each other. So what does that mean? That means that the customers have to really trust the foundry in collaborating with them in terms of products roadmap, in terms of new inventions that maybe they are still cooking within the company, but they're not willing to disclose to other people, especially their competitors. So foundry really needs to have this really high degree of trust between the foundry and the people who use the foundry. And so if a entity is no longer trusted, it would not allow them to be a viable foundry. That is really irrelevant. Okay, let me explain. In the past, maybe like 50 years or so, we have seen a tremendous improvement in semiconductor technologies, both in terms of the capability and the amount of things that it does, and also energy efficiency and speed and so on, that we have reaped a lot of benefits from these advances in technology, mostly driven by the need from society, because new capability and new energy efficiencies are desired in many of the products that companies produce. So I expect that to continue to happen. And in fact, not only to continue, but even accelerate, because we have been so dependent on continual advances of our technology. And many of the technologies are founded upon semiconductor technology. We talk about quantum computing, we talk about 5G, 6G, we talk about AI. Those all need semiconductor technologies to make their advances. So I expect the applications and the uses of semiconductor technology, and therefore the impact of semiconductor technology in society, to actually grow faster than before. And so there's a great need. And as you know, when there's a great need, innovation comes, right? When there's a great need, innovation comes, and there will be business opportunities. So I think those will not only continue on a path before, but actually accelerate because of the great need and great benefit that comes from it. Now, to the next question of how do you get those advances? In the past 50 years, we would maybe draw an analogy. We would like walking inside a tunnel. The way that semiconductor technology achieved its advances was by shrinking the transistors or the semiconductors from bigger ones to smaller ones. And that path has been so successful in the past 50 years that we are like walking inside a tunnel. That's the only thing you need to do. going forward, we know exactly what to do, no other methods or innovations required, just over there. Now we are at the exit of the tunnel. This path, just like everything that we do, any tool, any techniques, always saturate. And we reach kind of the end point of using this methodology. We're at the exit of the tunnel. Now there are two ways to interpret this. At the exit of the tunnel, you fall off the cliff and you're dead. You make no progress. Another interpretation is at the exit of the tunnel, you're not bound by the tunnel. You can go anywhere you want. And I think that's the excitement in semiconductor technology right now. We are at the exit of the tunnel. There are many ways to go. And because there is a strong need and innovation will come, and those innovations are not confined by what you can do in the past 50 years. Continual improvement requires research and development. And now, what makes good research and development? And that is the collaboration across different regions, different expertise is clearly important. Right? No one university is best in research, and you need many other universities to advance knowledge. And that's the same way with semiconductors. And you need many participants across the world, across the region. And we have seen many good examples of such collaborations happens really well. For example, within the US, actually, this is actually outside the US as well, the Semiconductor Research Corporation, which pull money from industry and fund university research, has been operating for the past maybe 20, 30 years. And it has a model for a well-defined objective and making a lot of progress in semiconductors. So those are one example. And another example, like the Inter-University Microelectronics Center, or IMEC, in Belgium. Those are a big consortium of industry that do advanced development together as a collection of, as a consortium. So those are very successful examples of international collaborations. And I believe that if the world could come together and coordinate and collaborate on the further R&D of semiconductors, we will be advancing the technology much faster than before.